Well, we've been thinking about finding unknown parts of an arbitrary triangle. An oblique triangle is one that's not necessarily a right triangle. And what we want to do is to find all sides and all angles for the triangle. Now, let me remind you what we've done in the past, how we write things. If we've got a triangle, an oblique triangle, so not necessarily a right angle, we're keeping track of sides labeled with the letters A, B, and C, and keeping track of angles so that the letter that labels the angle is a Greek letter that corresponds to the side opposite. So from A, we could label angle alpha opposite side A, angle beta opposite side B, and the third letter of the Greek alphabet gamma is the angle label opposite side C. So 6 interesting things to know about for an arbitrary triangle: the measures of the 3 angles and the lengths of the 3 sides. And what we want to do is to keep track of that stuff from information that's given. So we talked about the law of sines. The law of sines is useful if what you know in the angle, in the triangle, is 3 of 4 pieces of information, where the pieces of information are lengths of sides and measures of angles opposite the sides. Anytime you can do that, you can set up one of these ratios to have only one unknown in the equation. And with only one unknown in the equation, you can solve the equation to determine that unknown. Sometimes it's a 2-step process if it's the angle that you don't know. What this law of sines will give you is information about the sine of the angle. And then you need to know something about the inverse trig functions to recover what possible value the angle has from information about its sine. So the law of sines is good for case 1, that was SAA or ASA, and case 2 is for side-side angle. The other cases are going to be what's relevant for the law of cosines. If it is side angle side, 2 sides in the included angle, that will be a situation that the law of sines doesn't help for, and law of cosines will come in handy for that. And the other case would be if there are 3 sides known. So let's try some examples. The law of cosines is built from this. It looks like the Pythagorean theorem, which holds for a right triangle. It just has an extra term to allow for an arbitrary angle. And you'll see that there's 3 versions of the law of cosines. There is a version, the first version looks more like the Pythagorean theorem, because the labeling of the sides makes it look like C is the hypotenuse and A squared and B squared. A and B are the legs. Then with this term cosine gamma in between. Now think about that. This really is Pythagoras' theorem if it happens that you are applying the law of cosines in a right triangle, because the cosine of a 90-degree angle, cosine of 90 degrees, is 0. And so this correction term vanishes in that case, and you're left with just the version of the theorem that works without it. Then we've got 2 other versions. These are symmetrical versions, so that the first version, C and the angle opposite C, is there. It could be B, and if it's B, then it's the other 2 sides, and then the correction term is the angle opposite B, that's beta, and if it's A, it's the angle opposite A, that's alpha. So if you remember the form of this, you won't have to remember 3 equations to capture what you want. So here's an example: a side angle side triangle. If you lay out what a triangle looks like, we've got side B, opposite angle beta, so B is 3, C is 4, opposite angle gamma, and alpha is 40 degrees. So here's a situation. It is side, angle, side, and sure enough, if you try to solve this with the law of sines, you find that any way you can match up those ratios, you're going to have 2 unknowns in the law, and 2 unknowns make you can't come up with a value for what the you can't solve it with unless you have a single unknown in the equation. So solving the triangle means to determine the unknown parts. Since I know alpha and I don't know beta or gamma, those are 2 unknown things that I'll have. And since I know B and C, I have the only side A. So 3 things given and 3 things to determine. So let's go at this. We'll get the unknown side A first, and I can do that if I use the version of the law of cosines for A and alpha, because that will give me information that I can plug in for B, for C, and for alpha. So let's plug that in and we'll find out what A squared is. 3 for B, 4 for C, and 40 degrees for the angle alpha. Ask the calculator to do that, and the value comes out for A. It's A squared, so A squared is 6.614 something. And we can find out what A is. We get 6.615. That's close enough, let's say. And now I want the square root. You know the trick for the Windows calculator? There's no square root key on this version of it, the scientific version. But if you do inverse squared, that'll be the square root. So the value we get out is this 2.57 something. And sure enough, 2.57 something. So there's A, and now we need the other unknown things, the beta and the gamma. You should look at this, and with those 3 sides, triangles are rigid, so there's going to be a unique value that works. Let's calculate those. That's the information I have so far. So to get beta, I'll plug that information in for the version of the law of cosines that has angle beta involved. And I can solve by plugging in what I've calculated for B. Well, this was A. We calculated A. We were given B and C. So I'm going to take this equation. I'll add 2ac cosine beta to both sides and subtract b squared from both sides, and then divide through by the coefficient of cosine beta. That's 2ac. So we end up with an expression for cosine beta in terms of known numbers. Plugging in what I had for a squared, I didn't have to square root and then unsquare it and then square it back. I could take that value that I had for a squared directly, and plugging in these pieces for 2ac, a squared plus c squared minus b squared, and I get a value 0.6622. So let's do that 0.6622 and do inverse. It's set in degrees, so inverse cosine of that, and 48.5 something, 48.53 degrees. So there's beta. And now we don't have to do the law of cosines for gamma, because we've got the angle sum factor of the triangle, alpha plus beta plus gamma, have to add up to 180. So if we know alpha and we calculated beta, gamma has to be the extra bit. So here is 180, throw away what was given as alpha, throw away what we calculated as beta, and there's what gamma is. Let's try another example. A equals 3, B equals 5, C equals 7. That's a side, side, side triangle. So here is a way of labeling that. Those three things are known, and so I don't know the three angles. Let's grab them, and I can get them by using the law of cosines for each of two. Let's get alpha first. Alpha, opposite side A, beta, opposite B, gamma, opposite C. So A squared is B squared plus C squared minus 2BC cosine alpha. We know everything in this equation except alpha, so we don't know cosine alpha. But let's solve this for cosine alpha. Cosine alpha is A squared. Cosine alpha is B squared plus C squared minus A squared over 2BC. So plugging in the numbers that were given for A, B, and C, we get an expression for cosine alpha. Here it is in symbolic form. Here it is substituted in. And the value that comes out when you do the arithmetic is 13/14. 13/14 means that we want an angle whose cosine is 13/14. Calculator would tell us that. 13/14. And now we want the inverse cosine, and that's 21.7, 21.8 degrees. So that's the calculation for alpha. Let's do the same thing for another angle. That was the information given. Let's get beta out now. Same deal. It's going to be 11/14 as the cosine of beta. So we get an angle value for that. Pull out the Windows calculator and do it again. Do it yourself to make sure you can get that value. And now from alpha and beta, we can get gamma as from the angle sum fact. It has to be exactly 120 degrees. So we're solving triangles. Think about for a minute what would go wrong if you try to apply the law of cosines in this side, side, side case where the pieces of the triangle don't fit together. There's the triangle inequality that it has to be longer around than so the sum of any two sides of the triangle has to be bigger than the third side. If you try to plug in numbers for solving a side, side, side triangle by this recipe, what happens is if that law is violated, so for instance if this weren't 3, this were 1. So 1 and 5 as sides wouldn't stretch to cover the side of length 7. Those sides, 1, 5, 7, wouldn't correspond to any triangle at all. And the law of cosines goes bad in that situation by being by ending up asking the calculation you end up doing would be an impossible value for cosine, something outside the range of cosine. You'd end up with cosine beta is 1.1 or -3 or some crazy number. And that sort of makes the algebra and the geometry reflect each other. So that's enough to get you started. See what luck you have with these.